Before we start setting up the RBD simulation, let's optimize our fracture results a bit. So I'm just going to create a new section of my scene here, and I'll call that Week 3 Fracture Optimize. Then I'll dive inside and object merge in our previous fracture results, out fracture unfiltered. Now when we cached out these fracture results, we did an RBD pack to combine the fracture geometry and the constraints. So in order to do anything to our fractures, we'll have to drop in an RBD unpack to split out those sections. Now one of the main optimizations we'll be applying is size filtering, and we might want to use different size thresholds for each of the sections of that building. So we'll just use split nodes like we did before in the fracture process. And for the first one, maybe we'll check for the group to see if the path is equal to star, interior star. And I'll rename that and create another split. For the window frames, we'll check to see if the name is equal to star window star. See that isolates all of those. And we can drop in a null at the end for the exterior. Now for each of those various sections, we'll drop down a copy of our measure fracture HDA. Maybe I'll start with the exterior. And for the exterior of the building, we'll be seeing that a little bit more clearly than we will perhaps the interior. So we can't be quite as aggressive with removing little pieces. So you can turn on the size filter on your measure fracture, and you can see this default value of 10 is really deleting some very obvious sections of that building. All of the stuff visible here is getting called out. So we'll have to go very low with that. Even going down to 0.1 is deleting far too much. In this case, if you go down to 0.001, that's getting a bit more reasonable. But before we decide on a value, we should probably check the intact remainder of the building. So you can just drop in a null. I'll call this non-tiny exterior. Connect that to the second output of the measure HDA. And then we can see what those holes left behind look like. So I'll switch that to smooth shaded mode and zoom in a bit. And some of these holes are still looking like they're probably a bit obvious. And I'm going to go even smaller with this threshold. For this, I'll try 0.0001, which is not going to delete nearly as many pieces, but it will still optimize our fracture a decent amount. Even this tiny threshold is removing almost 4,000 pieces, and it's removing 65,000 polys. So even that very tiny threshold will give us a pretty decent optimization. Now one thing you could do with these tiny pieces, instead of deleting them, is to attach them to the nearest bigger piece. Now I don't usually bother with that. Usually I'll just delete them and you don't really notice in the finished shot, especially from the camera that's a bit further away. And you can also do some other hacks like perhaps render the intact building and then use some sort of a wipe as the pieces are simulated. But usually I just go with the simple solution and just delete out those tiny little bits because you typically don't notice it. Now once you've optimized the exterior pieces, you can do the same process for the interior and the windows. With the interior, I went a bit bigger to 0.0005 since we have a little bit more leeway for deleting pieces on the inside, and because that inside covers so much more 3D space, that's a much bigger savings. Deleting all these tiny little pieces is actually removing almost 50,000 unique pieces and more than 1 million polys. And for the window frames, I had to go with a much smaller threshold because it's easy for removing pieces to create gaps in the window frames. So I've only trimmed off a little bit with a pretty tiny value. It's only deleting 44 pieces and it's not very visually obvious. Now after removing the small pieces, we can do some additional optimization and remove pieces that only exist on the inside of the geometry. If none of the faces of a piece exist on that exterior, we can safely delete those without it causing any visual damage to our asset. Now, the way that I usually do this is by looping over each piece to detect whether it's entirely inside. So you can drop in a for each named primitive, connect our fracture geometry to that, and then we're going to do an attribute promote on the inside attribute that we set up in the fracture. So let's drop in that attribute promote, put it in the for each loop, and the original class will be primitive, new class detail, we'll be promoting that inside attribute, and we'll set the promotion method to minimum. And we don't want to mess up the original inside attribute, so we'll change the new name, call it inside only, and turn off delete original. So what this will do is if any of those faces have a value of 0, so inside equals 0 means it's on the exterior of the geometry, and that minimum promotion method means that once that's promoted up to detail, if it's anywhere on the exterior of the geo, it'll have a value of 0, but if it's entirely inside, it'll have a value of 1. But this detail attribute only gives us one value for the overall geometry, so we'll need to do a promote back down to primitives after promoting it up to detail in order to get that value to be on each piece individually. So we're going to change the original class for this second promote to be detail. The attribute name is inside only, and we'll push that back down to prims, and it probably doesn't matter which promotion method you use, but I'll select first match. Now for me this took about 30 seconds to run, so it's pretty quick, and to check the results at the end I'll drop a split node in, call this split inside only, and for that group I'll say inside only equals 1. So here you can see all the pieces that seem to be only on the inside of our geo. You can do a quick visual check if you perhaps template the node above to kind of take a look and see if that's giving us what we expect. That's kind of hard to see with all that dense geometry, but another thing that we can try is just dropping in a null from the second output of our inside only split. And then if you display that and compare it to the for each end just before the split, you should see no visual difference between the two since it's only deleting the pieces that we can't see. And if you middle mouse on that split node and look at the number of unique name attributes, you can see that's deleting another 1,359 pieces, which is another 160,000 polys. So it's another little bit of optimization that will save us some time along the way. And once we're done with this inside only check, we can delete that attribute since keeping these attributes around on the geometry can really slow things down and create bigger caches and etc. So just create that attribute delete, select that from the primitive attributes, and we'll call this null fracture optimized. And since we're done optimizing this, we can also go ahead and pack this fracture geometry. So we'll just drop in a pack node and we'll turn on this name attribute option. You can turn off this path attribute option here because we already have a decent path attribute that we're using. And you'll notice that this pack geometry doesn't have any of the underlying attributes promoted to each of those packed object containers. So you can use this transfer attributes option to promote any of those other attributes that you might want up to those packed containers. So we'll select bbox size, name, name orig, and path as the main attributes that we want always accessible on that packed up version. And we can also optimize our display and interactivity by just turning on bounding box mode for all of this packed geometry. And to switch that to bounding box mode, you can drop in a packed edit node, set the display as to bounding box, and add that in after the pack. So now we have this version that's much easier to work with in the viewport and will be much easier to sim and cache and etc. than it would have been with all of those extra pieces.